Question 19. A firework rocket is launched vertically. At the moment of explosion, it is moving with a vertical speed of 2 meters per second upward. The explosion releases an energy of 1 joule and the rocket bursts into 4 pieces with masses of M1, M2, M3 and M4, where the values are given there. The piece with mass M4 moves vertically upwards with a speed 1 meter per second. The pieces of mass M3 and M2 move horizontally, and the piece of mass M1 moves vertically. All velocities and directions in this question are given relative to the ground, and your answer should do the same. Not sure what lunatic would choose a different frame of reference than the ground, but each to their own. Part A. Obtain the speeds of all the pieces after the explosion. So this is an example of a question that has a fair amount to it, even if it's not completely obvious what the steps should be to answer the question in your head. I like to do a technique one of my friends in sixth form taught me, which was just throw maths at it, and what they mean by that, or what they meant by that rather, was just to write down some stuff that we know from the question, pull some equations that we think might be useful, and see where we get to. And in that process, you will probably find some inspiration. So if we just write down a few things from the question. So first, initially, we've got some mass, which will be M, which will be M1 plus M2 plus M3 plus M4. We know that it's this because we're told that it's a firework rocket and then it explodes into 4 pieces. So what will this be? This will be basically 1 plus 2 plus 3 plus 4, which equals 10, and that's all in grams. And we know that initially the vertical speed of this thing is 2 meters per second upward. So that's before the collision. And when I say collision, I really mean explosion. Next, let's think about the pieces that move vertically. So first, we are told that M4 moves vertically upwards afterwards. So that's M4 moves vertically upwards with a speed of 1 meter per second. We are told that M3 and M2 move horizontally, so let's just leave that for now. And then we're left with M1, which moves in some vertical direction. Though we aren't told which direction. So for now, let's just call it V1 going upwards. So first, let's just care about the vertical direction and do some maths. So the initial momentum will equal the final momentum by conservation of momentum. What does that mean? That means we have the initial momentum, which will equal the initial mass times the initial velocity, which in this case is, and now I'm going to write this in kilograms. So I'm converting the grams to kilograms just because when I do questions, I like to convert everything to standard SI so that I don't slip up. So that would be 10 over 1000 kilograms times by the velocity, which is 2 meters per second. And that is 0.02 kilogram meters per second. Okay, what about the final momentum? Well, that will equal mass times velocity plus mass times velocity. So the two vertical masses are m1 and m4, and so I've just subbed that in there. That should be clear. And then because we know that the initial momentum equals the final momentum vertically, so we're just caring about vertically at this point, it follows that 0.02 equals 4 over 1000, where 4 is this m4 mass, which was given in the question, plus the mass m1, which again we're told in the question is 1 over 1000 kilograms times v1. And then we can solve this equation for v1 by typing the numbers into our calculator, and you should find you get 16 meters per second. So that's good. We get a positive number out, and we've sort of implicitly defined upwards as positive. That tells us the velocity is of m1. And actually, we're only asked for the speeds, so we need not worry too much about the directions, but it's always good to have that in mind. Next, so this was all vertical. Next, let's do horizontal. So the initial horizontal velocity, momentum rather, is 0, because initially our trajectory is just going upwards. So there's no movement in the horizontal direction, so we know that the horizontal momentum will be 0. And the final horizontal momentum will be given by the two masses that move horizontally, which we are told is m2 and m3. And we know that one of them will go this way and one of them will go this way, because that's the only way we can sort of conserve momentum back to 0. So for now, let's not worry too much about what the directions are. Let's just do the maths. So the final momentum will be m2 v2 plus m3 v3. And subbing in the masses, we have 2 over 1000 v2 plus 3 over 1000 v3 equals 0, and this gives that 3 lots of v3 equal minus 2 lots of v2. So that's one equation that we've just created that relates v2 and v3. Now, using energy or conservation of energy, so using this other bit of data we're given in the question, we can formulate another set of equations so that we can find out what v2 and v3 are. So what do we have? Well, we have the kinetic energy before the collision, or rather the total energy before the collision must equal the total energy after the collision. Initially, we have just kinetic energy, and then afterwards we have the sum of all of the kinetic energies minus the energy released. which we're told is 1 joule. So hopefully that makes sense. Just to reiterate, initially we have the object just moving upwards, and the only energy here we need to consider will be the kinetic energy of this object moving upwards. Then we have an explosion, which releases a bit of energy, and then we have 4 masses going in various directions. So we need to sum up these masses' kinetic energies, or rather the kinetic energy of each of these masses. So hopefully that energy equation makes sense. So now it's just a case of subbing in the numbers. So what do we get? We get a half. The original mass we worked out earlier is 10 grams. So that's 10 over 1,000 kilograms times by the initial velocity, which is 2 squared. Next, the sum of all of the kinetic energies. So we've got m1, which is 1 over 1,000 times 16 squared, which we worked out earlier. Mass 2, which is 2 kilograms, which is v2 squared, plus mass 3, which is 3 grams, or 3 over 1,000 kilograms, plus mass 4. And we're told that mass 4 goes at 1 meter per second. So that's just 1 squared. And then we have minus the 1 joule, which is the energy released. And you should find, if you turn the handle and do all of this algebra, you end up with 2 lots of v2 squared plus 3 lots of v3 squared equals 1780. And we'll call that equation 2. So now we basically have 2 equations and 2 unknown variables, v2 and v3. So what we can do is solve those equations. And again, I'll leave the algebra up to you to solve these 2 equations. Do practice that. And what you should find is you get 2 solutions. Because if you think about it, this equation 2 is basically sort of a circle, kind of. And then we've got some sort of straight line. So this isn't necessarily what it looks like, but basically what I'm saying is there should be 2 different solutions. So what you should find is you get v2 equals 23.1 meters per second and v3 equals 15.4 meters per second. Now, what's special about that? Apologies if you can hear the wagon leaving the shopping centre near where I live. Right, that should be gone now. So here we have some funny signs. What does this mean? Why do we have sort of 2 solutions that are one is minus, one is plus? Well, the information, we're not really given enough information in the question to know which way around the masses are. So let me explain. We know that the masses must be going sort of apart from each other, because that's the only way we can then have a net 0 horizontal momentum, which is what we need because there is no initial momentum. But we don't know if mass 2 is going to the left and mass 3 is going to the right, or mass 3 is going to the left and mass 2 is going to the right. We don't have enough information to make that judgment. So what the maths tells us is exactly what we think should happen. We get a minus when we get a plus, and we get a plus when we get a minus, which is basically saying they need to go in opposite directions. But we do have freedom over which direction that is because, again, we're not given enough information in the question to make that judgment. Thankfully, we are only asked for the speeds anyway, so you need not give the plus minus, but here are the speeds. Next, part B. Higher speed pieces can be obtained if the directions of the movement of the pieces are different from those in part A. Under which choice of directions would the maximum speed of one of the pieces be achieved? So initially we have an upward momentum, which must be conserved. Now we have 4 sort of masses, and intuitively it should be clear to you that we want the lightest piece to go upwards, because then it will go upwards sort of the fastest because it's lightest, and we want all of the other pieces to go downwards. And this configuration will give the maximum speed of one of the pieces. So hopefully that makes sense. Basically, we've got one piece here initially that's traveling upwards. That then explodes. If we want the maximum speed of one piece, well, first we take the lightest piece because we know that momentum is sort of mass times velocity. So smaller the mass, higher the velocity. So we want to take the lightest piece. We'll say that can be traveling upwards. We take all the other pieces, have those traveling downwards. So it should be intuitively clear to you that that's the configuration for which we get that, or rather, this is the choice of directions that would give the maximum speed. If that's not intuitively obvious to you, I recommend just testing out different configurations of different numbers by just saying you start off with the velocity, the momentum of 0.02, and then you basically have m1 v1 plus m2 v2, etc., and just plug some numbers in and try and find which one gives the biggest v1, and you should find it's when all the other v's are negative. Okay, I think I've basically answered these questions, but thank you for listening.